Hi guys, I wanted to make a video dedicated to potential energy graphs, which I know can be one of the trickier parts of the work in energy unit, but hopefully this video is helpful. So the first thing to notice about this graph is this neon green line that I have going through the graph, and this line is equal to my mechanical energy. So my mechanical energy is just equal to my potential energy plus my kinetic energy. So my mechanical energy can be thought of as my total energy in the system. And something to notice is that mechanical energy is always constant, and this has to do with conservation of energy. So the next thing to notice are the points on our potential energy graph where it looks like the slope of the graph is either 0 or about 0. So that would be here at this minimum, and here, I know this isn't drawn the best, but where it's kind of tapering off to just be a flat line where the derivative would be 0. So whenever you see a relative minimum in a potential energy graph, that point will be something called a stable equilibrium point. So that's a stable equilibrium. And this is the point where the particle would be most stable. And whenever you have something that's a maximum, or basically the derivative is 0, but it's not a relative minimum, like this point right here, that's an unstable equilibrium point. And the way that you can think about this is, imagine if I put a particle, say, right here. It's much more likely to fall down towards stable equilibrium than it would be to somehow climb up to my unstable equilibrium point. So when you think about displacing the particle along this potential energy curve, think about where this particle is most likely to fall, and that would be your stable equilibrium point. The next thing to notice on a potential energy graph is that the difference of my mechanical energy, which is this much, minus my potential energy, which would just be this much, where whatever this value is here. Well, right in here, this is my kinetic energy then, because my kinetic energy is just equal to my mechanical energy minus my potential energy. And the same can be done to find potential energy if you do mechanical energy minus kinetic energy. And we can see that in our equation up here. Another thing to note about potential energy graphs is that from a potential energy graph, you can always find or sketch the derivative of the curve, or of the potential energy function, I should say. So we know that potential energy, well, we know that this is the negative integral of force times dx from some initial x to some final. And so what we can say is that the force then is just equal to the negative derivative of potential energy. So along this line, if I were to sketch my force, well, I can immediately put zeros where we know this line is flattening out, and then we could say, well, say the slope here is about -2, then I could put a point at +2 because force is the negative derivative. So if this is -2 and this is my slope, then I would do slope times -1, and that would give me force. So that's how we can use the information from a potential energy graph to find, or at least sketch, a curve of force. So I hope this information was helpful. Before I finish, one more thing is that a particle can get stuck between 2 points in this potential energy curve and kind of get stuck rocking back and forth between these 2 points if it doesn't have enough energy to get over this curve and get into this part of the graph? That's a question that'll sometimes come up on the test, although I haven't seen too many cases of that. I hope this video was helpful, and I'll see you in my next video.